Lesson 10, AC Circuit Analysis. Let's start section 10.1, Linear Elements and Linear Circuit. Let's assume that the relationship between the voltage V and the current I of a circuit element is given by V equals Fi. Here, F is a function, and V and I are time-varying variables. An element is linear if and only if the function f has this property, where a1 and a2 are constants. Resistance, inductance, and capacitance are linear elements. Because the voltage V and current I relationship of a resistance R is V equals Ri, and this relationship satisfies the property of linear elements. In the case of inductance, the relationship is given by V equals L di dt. This satisfies the property of linear elements. Capacitance also has the property of linear elements. We can ignore the integration constants, because we are dealing with the steady state, in which the transient responses caused by the integration constants have dissipated. Next, let's consider the case where V and I are complex numbers. The condition for a linear element is expressed in the same way as in the case of time-varying variables. Resistance, inductive reactance, and capacitive reactance are linear elements. Because voltage V and current I relationship of a resistance R is V equals Ri, and this relationship satisfies the property of linear elements. In the case of inductive reactance omega L, the relationship is given by V equals J omega Li. This satisfies the property of linear elements. Capacitive reactance negative 1 over omega C also has the property of linear elements. This is a voltage source. This is the symbol of an ideal voltage source. Lowercase v represents an instantaneous value. A load is connected to the voltage source. Lowercase z represents the value of the load, and the current I flows through the circuit. Note that the voltage V of an ideal voltage source is independent of the current I. In the bottom figure, uppercase V, uppercase I and uppercase Z are complex numbers. Z represents the impedance of the load. If V does not depend on I, then the source is called an ideal voltage source. Let me introduce a new circuit element, the ideal current source. The arrow indicates the direction of the current. The lowercase I represents the instantaneous value of current. When a load Z is connected to the current source, the voltage V appears across the load. The feature of an ideal current source is that I is independent of V. In the bottom figure, uppercase I, uppercase V and uppercase Z are complex numbers. The current I of an ideal current source is independent of V. From now on, let's focus on the analysis using complex numbers. A practical voltage source can be represented with an ideal voltage source V0 and an impedance Z0. Z0 is called the internal impedance. The terminals A and B are the output of the practical voltage source. In this case, the terminals are open, so the output voltage V equals V0. If an impedance Z is connected to the terminals A and B, then current I flows, and V becomes different from V0. The output voltage V equals V0 minus Z0 times I. A practical current source can be represented with an ideal current source I0 and an admittance Y0. Y0 is called the internal admittance. If an impedance Z is connected to the terminals A and B, then current I flows, and I equals I0 minus Y0 times V. If a circuit consists of only linear elements, voltage sources, and/or current sources, it is called a linear circuit. The circuit in the box has L linear elements, M voltage sources and N current sources. The numbers of voltage and current sources could be zero. Even if we do not know the connections inside the box, at least, we can say that this is a linear circuit. Exercise 10.1.1. Show that if V0 equals Z0 times I0, and Z0 equals 1 over Y0, then the practical voltage source and the practical current source are equivalent. The answer to exercise 10.1.1. The output voltage V of the practical voltage source is, V equals V0 minus Z0 times I. If V0 equals Z0 I0, and Z0 equals 1 over Y0, then V becomes I0 minus I, over Y0. Then, this equation is reformulated to express the output current I for the practical current source. Exercise 10.1.2. This is your homework. Pause the video and find the internal resistance R0 of the signal generator. Pause the video, and find the current source I0, and the internal conductance G0. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.